Okay, and now we're going to hear from Peter Grube with Northwest Aero Barrier, product you've heard about a little bit from Perry. Take it away, Peter.
Thank you, Don, and thanks, Perry. Such a cool project that you're working on, and a great presentation of how it all works. So as Don said, my name is Peter Grube, and it's a pleasure to be with you today for the Go Clean Energy Conference. And very cool to be on the panel for Net Zero Energy Homes because their time has come. A little background on me. I'm a certified sustainable building advisor with over a decade of experience in the residential building industry, working on green, high performance, and sustainable homes. I am also an owner of Northwest Aero Barrier, an innovative air sealing technology that makes stopping air leakage in building envelopes quicker, easier, and more reliable than ever before. My message today is that effective air barriers matter because they are critical to better buildings, and better buildings are good for people and the planet. Before I go any further, I will quickly mention ventilation. While my focus here is on the benefits of air barriers, it is critically important to highlight the fact that an effective air barrier must be accompanied by mechanical ventilation. We saw in Perry's project that he's using a life breath ERV. That's best practices. Build it tight and ventilate it right is the formula for sustainable buildings. My light bulb moment around just how much air barriers matter came when working on one of the first net zero energy homes here in Central Oregon over 10 years ago. Our team was in the design phase of the project, focusing on the house's energy model with our third-party certifier, Earth Advantage. To build a net zero energy house affordably, we were tweaking the heck out of the building variables to get the energy load, represented by the energy performance score, as low as we could. We tried modeling everything from incrementally increasing wall thicknesses to ever more expensive window packages, until finally someone suggested reducing the air leakage metric in the model. And voila, all the pieces came together. Not only did we see a significant drop in the energy load of the home, allowing us to reach our net zero performance goals, but it would be much less costly and easier to implement an air barrier than extremely thick walls or extremely expensive window packages. All that, and we would have better control over the indoor air, so the home would provide superior indoor air quality and be more comfortable year-round. Reducing the envelope air leakage was the silver bullet we were looking for. I had a number of geeky learning objectives, but only 10-minute time limit, so I'm consolidating them into this one takeaway. Better homes, and especially net zero energy homes, need to control air leakage with an effective air barrier. If nothing else, remember this hashtag for better buildings. Don't be an air hole. What the heck is an effective air barrier, and how do you know if you have one or not? The air barrier is one critical component of the 4 primary control layers of a building envelope. In its essence, the building envelope's job is to separate the out of doors from the indoors. An effective envelope is made up of these 4 primary control layers, listed here in order of importance to the sustainability of the building and directly related to risk management for the builder and homeowner. First and most importantly, the bulk water control layer. You've got to keep the bulk water out of the house. Followed very closely by the air control layer. Stop uncontrolled air leakage. Then the vapor control layer, keeping water vapor out of the walls. And finally, the thermal control layer, insulate it. My focus is on the air control layer, or air barrier. The air barrier's job is to stop air leakage between the conditioned space and the unconditioned space, as defined here by the continuous red line. Picture the air barrier as an inflated balloon, keeping interior air in and exterior air out. Notice that the vented, unconditioned attic and the unconditioned garage are on the exterior of the air barrier. Also notice that the red line is continuous, which is essential. The test of an effective air barrier at the design phase is called the pencil test. That's when the architect and builder can put a pencil down on a cross-section of the plans and trace the intended air barrier without having to lift the pencil off the plans. If at any point or points the pencil has to be lifted for even a split second to get around the entire air barrier, it is no longer continuous and therefore not effective. Back to our balloon analogy, any holes in that balloon's skin will render it ineffective. Giving a set of plans the old pencil test sounds easy enough. However, in the real world of construction, many homes do not have effective air barriers. They're really leaky. It's actually extremely challenging to limit, identify, and mitigate all the opportunities for uncontrolled air leaks in building envelopes. The biggest culprits, as identified in the image on the left, are holes and gaps in the floors, walls, and ceilings, about 30% of the air leakage. These occur during the framing phase and with penetrations made during the installation of electrical, plumbing, and mechanical systems of the house. Other big culprits are the ducts, especially through unconditioned space, fireplace inserts, gaps around doors, operable windows, and big patio sliders. How can you know if an air barrier is effective or not? During the design phase, you use the pencil test, but out in the real world, the only way to know for sure is by testing using a device called a blower door. I can tell you from experience that visual inspections simply do not work. If you don't measure, you don't know. A blower door is basically a large fan which depressurizes or sucks out the conditioned space of the house and measures the amount of air leaking in through the building envelope. That measurement is given in the industry standard metric of air changes per hour, or ACH. Wait, what's an ACH? I'm glad you asked. An air change per hour, or ACH, is the number of times the total volume of air inside a house is exchanged with the air outside the house under a given pressure in 1 hour. So let's look at this example. If a house is 2,000 square feet and has 10-foot ceilings, it would have a total volume of 20,000 cubic feet of air. Picture 20,000 individual 1-foot cubes of air packed inside the conditioned area of this house. When there's any pressure change, usually from wind, those 20,000 cubes of air start to leave the envelope, being replaced by air from the outside. To give you an idea of what this means, we would shoot for a net zero energy home like Perry's to have 1 ACH, meaning with a steady pressure of approximately a 20-mile-per-hour wind, the total volume of air in this house, or 20,000 cubic feet of air, would move out of the house once each hour, replaced by the outdoor air. So that's a manageable amount of leakage in 1 hour. Not a lot of work for the heating, cooling, or ventilation systems, and not a lot of potential hot, cold, smoky, or otherwise polluted air coming into the house. However, if you take that same house and have the typical uncontrolled air leakage rates of today's new homes, around 5 ACH, you now have 100,000 cubic feet of air moving through the house every hour. That's 5 times the energy wasted, 5 times the work for the heating, cooling, and ventilation systems, and 5 times the hot, cold, smoky, or otherwise polluted air coming into the house. Well, how about an older 70s ranch home that gets a blower door test of 12 ACH? 12 times the air changes. You start to understand the magnitude of the problems that arise. You may have even experienced them yourself. The expectations of a building determine the level of effectiveness required of an air barrier. Here's what I mean. A winter warming hut with 1 wall open and an ACH of 50 would be expected to keep you alive overnight. It's doing its job. An old homestead that actually has doors and windows and an ACH of 25 might be expected to keep out the wild animals and provide year-round survivability. A Brady Bunch house with an ACH of around 12 would be expected to provide basic year-round livability, but you'd still have to put on a sweater in the winter, swelter in the summer, fill with smoke during forest fire season, and will likely start needing siding and roofing repairs in 15 to 20 years. a high performance home with an ACH of 2 is expected to be very energy efficient, provide high levels of year-round comfort, high quality indoor air, and remain extremely durable. A net zero energy home with an ACH of just 1 has very high expectations for building performance. We expect minimal energy use and no power bills ever. We expect the highest levels of clean, healthy indoor air and year-round comfort. We expect long-lasting durability. And most importantly, for the health and well-being of the planet, we expect very low operational carbon footprints because the energy is being supplied by clean, renewable power. In summary, I hope you've had your light bulb moment about air barriers. Help me spread the word. Effective air barriers matter for better buildings because better buildings provide for the health and well-being of people while enhancing the health and well-being of the planet. The time is now. Thank you so much.
Thank you, Peter. That was tremendously informative. Much appreciated.
Hope it helps.